I'm here to present my summer HuBMAP internship project. For a little bit of background, I'm a rising senior at the University of Texas at Arlington, majoring in data science with a concentration at psychology. For this summer, I have been placed at the High Dive Lab at the Harvard Medical School Department of Biomedical Informatics for the HuBMAP internship. Before I begin, I assume everyone here must have interacted with the HuBMAP data portal to some extent, or at least heard about it. But for those of you who are unfamiliar with the data portal, it is an open platform that allows you to discover, visualize, and download healthy single-cell tissue data. For my project specifically, I am looking for 2D and 3D imaging data modality that is multiplexed. Multiplexed means when there are multiple different images and each of them representing a protein or a biomarker stacked on top of each other to create this multiplex image. I'm also looking for data which has at least 10 or more channels. When interacting with the data in the HuBMAP data portal, you come across these visualization views that allow you to explore the data and also change the different settings and view different protein markers. This is created by VITESS, which is a visual integration tool for exploring single-cell experiments. But for this project, I'm specifically looking for VITESS, the application of VITESS in the HuBMAP data portal for these interactive VITESS widgets. Now, one of the main issues with VITESS is that despite being a powerful tool, it can be overwhelming for new users or beginners to understand what all of this information means. So for someone who may not have experienced this kind of data before, it might be difficult to understand what these different protein markers here mean or what these different regions indicate. An important thing to note here is that this image here is just a mock-up, and the data set reflected in this is not currently available on the HuBMAP data portal, but is very relevant to my project. So what if we could have an LLM-powered chatbot or a chat window that can allow users to ask what these different protein markers mean and see those settings and these different regions that are interesting to look at? So my research goal for this internship was to integrate GPT into the VITESS views in the HuBMAP data portal for easier navigation and analysis of 2D and 3D imaging data. And it's one of the reasons why we're using LLM is that its biggest advantage is that it supports natural language interaction. Natural language is more intuitive and user-friendly and allows users to ask more vague or casual queries such as, can you show me healthy cell markers, or can you show me good and bad cell markers? This is especially useful for students who might use the data portal for learning about these different data sets and using it as the first step to explore this data. To give you a better idea of this, let me show you some example of some general marker queries. Here is an example of a user asking, can you show me MART1? The LLM responds back with a description of what MART1 is and goes ahead and changes the control settings to display that specific marker. Another example is if you ask it, can you show me healthy cell markers? In this case, you don't necessarily need to specify which protein markers are of interest, but it can identify which of these are available in the data and display those markers to you. Here's another example of this with the spleen codex image where I have asked, are there any B cell markers available? And it can identify which B cell markers are available in this data set and then go ahead and select those markers for you. But here's also some more examples of some region-specific queries that you can ask GPT or the LLM. This is an example video demo of me interacting with it in a Jupyter environment where I have asked, can you show me region with markers that indicate active angiogenesis? And so it returns you the coordinates of all those relevant regions that show you active angiogenesis. And it also gives back a description of what markers are associated with this. And if you look here, it goes ahead and zooms into that region, into the topmost region where angiogenesis is displayed. Another example of this in the Jupyter environment is, can you show me a region with high concentration of T cell markers? As you can see here, it once again provides you the coordinates that are relevant. And it also gives you a description of what T cell markers are and what their functions are, and zooms into the region of the most interest of these T cell markers. So how does this all work? The way it starts is that a user asks a query. This can be something like, can you show me S100A, or as shown before, can you display T-cell markers? An API request is made to GPT and the query is provided to it along with the system instructions. For my current project, I have only tested this with GPT 3.5 Turbo and GPT 4.0 without any fine-tuning. The response that is sent back from GPT is parsed into two parts, the description and the configurations. As you can see in this example here, the description contains information about what CD4 is, and then the configurations are it gives you configurations which is sent to Vitess to update those settings. What this looks like to the user is that you can view the description of those markers in the chat window, and those configurations are sent behind the scenes to Vitess for it to update. But there are two more things that happen when an API request is made to GPT. First, it assesses if a general marker-related question is asked. If yes, then it follows a set of instructions that I have provided to it and provides the response. But if a region-based query is asked, then GPT calls a tool and obtains the coordinates for the regions and then follows the system instructions. So what are my system instructions and my tool? Well, my system instructions are the prompt that I have provided GPT to follow. You can see here that this prompt is broken down into three parts. The first part is the general guidelines, where I have told it to always provide an answer in exactly 2 paragraphs and no more, and also to look up the marker name from the channel name dictionary that I have provided to it. The second part is an example of what the Vitess configurations look like so that it always follows that exact structure. And third, I have provided a channel name dictionary so that it only looks for the channels or markers that are present in the image and not for any outside of those. Now, before I explain what the tool is, where are these regions exactly coming from? Now, if I were to normally look at the image pixel by pixel and find the most interesting regions, that would be extremely time efficient in real time. To make this process a little more simpler, this image is broken down into multiple different patches or tiles, and more higher level statistics is calculated for these different markers on their concentration. What an example of this will look like is that if a user asks, can you show me a region with high concentration of CD4 and CD8 markers, GPT will provide those, look up those channel IDs and the region. It will pass that to my function, and then that function will return me the coordinates, the XY coordinates of those interesting regions, and update that in Vitess. In conclusion, my main contributions for this project were to allow user to ask 2 levels of queries. The first one being general marker-related queries, where you can ask it to show you different protein markers. And the second being asking it to show regions of different high concentrations of different combination of markers. And third, it also, my other contribution is that it can control Vitess views dynamically based on user queries. To think about some of the limitations, GPT is non-deterministic. This means that it is not always consistent with its responses. Here, I have showed 2 examples of the response it has provided me when I asked it, can you show me T-cell markers? While both of these responses are correct, in the second one, it has also mentioned an additional marker that it did not the first time I asked it. This can easily be solved by further prompt engineering and giving it more guidelines. So this can be something like asking it to identify all the related markers from the channel dictionary provide, and to provide information on all of them and display any 3 if available at all times. We can also provide GPT an instruction to ask the user if they'd like to view all of those markers or only a select combination of those. Now, another thing that is very important to think about with LLMs is hallucination. Hallucination is when LLMs can provide incorrect or false information, which can be very harmful. But I want to talk about how for this approach that I have used, there is a very low risk of hallucination. The reasons for this being is that I'm not using the vision capabilities of GPT, but in fact, I am providing it all the database and channel information. This allows me to check if the answer provided by GPT is correct or not. Third, another reason why there's low risk of hallucination is that we have only asked low-level queries and not asked it to perform any form of analysis on its own. But it would be useful if another way to kind of even reduce the chances of hallucination is to provide it information associated with the data. If we could provide it maybe a publication or a paper that is associated with a specific data set, we can ask it more specific queries. Like for example, over here, you can ask the user, you can ask GPT, what am I looking at here? And it will return information exactly specific to that data set. Second, I can also ask it something like, what is unique about this data set? And it will look back into the paper and tell us what is different about this data set or what is unique about it. This is specifically useful for students who, once again, are interested in learning more about this data, or they have no idea what is unique about this data set in comparison with other data sets. For future work, I have talked about some of the limitations that I do plan to address, but I still have 3 weeks of my internship remaining, and I would love to hear some suggestions or ideas from the rest of you on anything you would like to see or for this project. I would like to thank the Soldier Lab for providing the 3D decisive data, the HuBMAP Summer Internship Program, HuBMAP Consortium and NIH, and also the High Dive Lab at Harvard Medical School. If you're interested in interacting with the specific data in the Jupyter environment, you can scan this QR code to access that collab. Thank you. Are there any questions?